Okay, good morning, ladies and gentlemen. This is Resh Mahaber. We are going to talk about, coming from Wayne State University. This is, again, a continuation of my segment of Math 1800, which is pre-calculus. And we're going to start on where we call Chapter 4 in our textbook, which is exponential functions. Now, we've talked about all kinds of exponential functions. Give me 1 second, make sure of something here. Beautiful. We've talked about all kinds of exponential functions. I mean, not exponential, but all kinds of functions. For example, oops, I have my computer's doing all kinds of things. First thing we've talked about, that's not the right color I want. Let's go to black. You guys need fanciness. We'll go back to black. We've talked about all different kinds of functions. We've talked about the classics. What my classics is linear. Linear are your guys that are y equals mx plus b. Those are your straight line ones, or also called degree ones. Easy, right? Then we got guys that are in your nonlinear family. So these are all the different guys. I'm just going to list them all in order. We've covered them. Quadratics. These are the guys that are in the form y equals ax squared plus bx plus c. These are guys that quadratic formula works on, and are typically your degree 2s. Are your degree 2s. Then we talked about everybody else that are polynomials that are even higher than that. So we'll say higher degree polys. Okay. Now, I don't know how high you've gotten. I think in my entire life, I've only worked up with like a degree 7. So they can get pretty big, but for any function you have, those are the guys that look like, I don't know, ax to whatever power you want plus stuff all the way to some n power. I'll call it b, right? So they could be really, really big, and that's degree bigger than 2. So these are degree, the degree of that function is bigger than or equal to the third degree. So we got degree 1s, degree 2s, and everything bigger than degree 3s. These are all polynomials. And then we just got done talking about rational polynomials. Oh, rational functions. Rational. I can't spell this morning. Rational functions. Okay, and my handwriting is just equally as bad. Those are the guys where you're basically dividing two polynomials. Boom, 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 boom. So like that, what that means is, for example, just to reiterate, we have a numerator that's like 2x plus 1 and 3x plus 7. Make it a square just to make it different. Okay, so this would be a rational polynomial. Okay, so this is something else that a rational function, right? And don't forget that p and q are both polynomials. So p and where this guy is a polynomial, and this guy is a polynomial. Pretty easy, right? Rational means fraction after all. So what's next? Well, let's talk about what's next. Next thing is, first thing we're going to talk about is this first guy called exponentials. And I'm going to take it very slow so you can kind of get an idea of exponentials. All right, so exponentials are not very, very bad. So what is an exponential? Okay, a polynomial is when the base is changing. So here's a polynomial. Polynomial is when the base is changing. Okay, so it's like we don't know what the base is, and the exponent is a number. Well, an exponential, the difference in the two is that an exponential is the flip of that. It's where we don't know what the exponent is, but we know what the base is, and the exponent is changing. Now, here's what you got to know about exponentials. Exponentials are one of the most aggressive functions out there, meaning that they grow really, 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 really fast. Interest rates, you know, like how we charge interest with people, it's kind of how we make, is kind of based off of kind of based off of an exponential function. So that's why if you ever take out like a student loan, make sure you pay off the interest, because you don't want the exponential part of that student loan to kick in. If it does over long periods of time, you'll never catch up. You'll always be underwater. Okay, so let's graph this guy. Okay, just so you get an idea of what it is. This guy, exponential functions are a lot different, and I want to keep using the word exponential so you get used to hearing the word exponential. But exponential functions, thank you, I appreciate it. Oh my God, it really wants to, doesn't it? Your computer needs to restart in order to finish this. Okay, thank you, I appreciate it. Okay, it really wants to do it. All right, I'll let it figure itself out. Hold on 1 second, guys. Perfecto. Oh, close it. Bingo. Okay, so exponential functions. Let's graph this guy. Okay, now how do we graph exponential functions? And I was saying that this guy is a little bit different. It's different, exponentials, and the next one we're going to talk about is logarithmic. Exponentials and logarithmic are very closely related because they undo each other. But they're the only two graphs that have asymptotes. Only two graphs that have asymptotes. So I'll let you figure out where this guy's asymptote is. So when we don't know how things look, when we don't know how a graph looks, what do? We plot points. So here we go. Here's x. Here's f of x. All right. And then here's my graph. Okay, so you look at this, you say, okay, there aren't any domain restrictions, right? There's no denominators, there's no even roots, there's no logarithms, so I can plug in any numbers I want. So let's just plug in some whole numbers here. I'm going to plug in 0. That seems like a good starting point. When you plug in 0, 2 to the 0 power is 1. 1 is going to be 2. 2 is going to be 4. 3 is going to be 8. It makes good sense. So 1 is 1. Whoops. I can't do math today either, apparently. That's 1 point. 1 is 2. 2. And you kind of see this. It's kind of like doubling each time. You see how huge this is getting? Okay, and why is it doubling each time? It's based off of that base. It's a double, right? It's a 2. If it was a 3, it would triple. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Right? 1, 2, 3, 4, 5, 6, 7, 8. Got it. All right. So you kind of see the function going up this way, like so. Right? But we just said there's no domain restrictions, so we have to contemplate what's going on this negative side. So let's see here. Go back to black. And, well, what's over here? Negative stuff. So if we plug in -1, here is something to keep in mind. When you plug in a negative number into a function that is exponential, what is a negative exponent? Going back to your basic algebra skills, you know they are fractions. This will be -1/2. This would be 1/4. All right, we'll plug in -3. It'll be 1/8. So when we plug in -1, we get halfway there. When we plug in -2, we get halfway there. When we plug in -3, you get 1/8 of the way there. So here's a question. Will there ever be a number that I'll plug in to hit 0? Will there ever be a number that I'll plug in to hit 0 on the y's, which will basically be right on top of your x-axis? Answer, no, because there is no exponent that's going to give you. So 2 to what power is going to be 0? Nothing, okay? But here's the point. If you look at the numbers, it's creeping. It's getting closer, 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 and closer. We call this being asymptotic. Hence why I said there's an asymptote somewhere on this graph. It's never going to hit 0. It's going to stream out forever. So now I want you to use your common sense. After we've already discussed horizontal asymptotes and vertical asymptotes, I want you to think about this. Does this guy have a horizontal one or a vertical one? If it was vertical, this line wouldn't clip it. So it doesn't have a vertical one. Obviously, the only place it has a horizontal asymptote will be right here at this line. And we already talked about that. The graph of horizontal lines, it has the equation y equals. So this is y equals 0. Done. This is what now here's something that's cute. This is what every exponential will look like, okay? Every exponential. I don't care. So in general, I know this one was for 2 to the x. In general, here's what any exponential, f of x equals a to whatever power, will look like this. And I've been using Desmos a lot. It's a graphing program online. Let's see if I can access that really quickly. And if I can, then I'll show you. Desmos. Start graphing. And I've been telling you that it's going to look exactly the same, right? So you guys choose. So here's 2 to the x, the one we just did. Bingo, right? Horizontal asymptote going through the x-axis, right? It goes through 1, right? We talked about it. Now watch this. I'm going to compare that. I want you to give me another graph. Give me another graph. Oop, that's not how you do it. There we go. Let's do it to 3 to the x. You see something? It looks exactly the same, exact same horizontal asymptote. And guess what? It still went through 1. Isn't that something? Why? Because 3 to the 0 power is still 1. What if I did 4? Oops, 4 to the x, not 0 power rush. All right, and if you notice, guys, it's going to look exactly the same. Okay, what if we did something that's weirder looking, like I don't know, 27, random number. Same thing, right? So it's horizontal. The only thing that's going to change is that bend. And you'll be able to determine when these bends happen when you guys hit Calc 1. But as of right now, all you need to know is that all exponentials look like this kind of graph. Okay, so let me minimize this if it'll let me minimize it. All right, so all exponentials look like that kind of graph. So in general, this is what you need to know. All exponentials go through the point 1, 0. So sorry, 0, 1. Have a horizontal asymptote going at the x-axis. So the spacing here should be 1, and I'm emphasizing on the spacing, and then it's going to hug the horizontal axis on the negative side. It's going to touch that, and it's going to spring up. Okay, so this is every graph that you're going to see. There's no if, ands, or buts about it. Okay, so pretty easy, right? Okay, so now that we got this, let's recall something that is very, 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 very sneaky. And what do I mean very, very sneaky? Remember chapter 2.5. I told you guys that this is always going to come back. These are when we did transformations. And I told you that if you have a graph, then guess what you could do to it? You could shift it left, right. You can flip it up, down, you can flip it left, right, and you can shift it up, down, right? Well, we just got a new graph. These are transformations. So recall this, okay? And I'm going to recall the order for you. So in order to transform a graph, the order, and I always told you guys to draw 5 graphs or 6 graphs, depending on how complex the function was. Okay, I'm still going to stick to that, okay? The order of transformation is as so, okay? 1, let me switch to black. I think black's good. 1 is your left, right, shift, okay? 2 is your flips, and you have 2 different kinds of flips. You can flip left, right, or you can flip up. Ooh, that's the ugliest arrow I have ever seen. Or you can flip up, down, okay? 3 is your up, down shift. Okay, and don't forget, all this comes after you've determined, I'll pull a step 0 here, what the basic graph is. Because don't forget, we've already determined tons of graph. We have absolute values, we have quadratics, we have cubics, we have linears, we have square roots. What else? Have we done anything else? No, but now we have a graph that looks like that. You notice that I left the axes off of all of these. That's an exponential, obviously, we just did those. But I left axes off all of these because you can take this and we're shifting the shape of the graph. Okay, so I feel we should do an example. This is actually being a pretty short video. I thought it was going to be longer than this. So let me show you how to diagnose these or find them in everything else. So here we go. Let's say example, and I'm going to try to write extremely neat, even though I know I struggle with it. F of x. Let's say I said graph this. F of x equals, oh, I have 2 perfect examples to show you guys. Minus 3. Okay? F of x equals 2 to the negative x plus 2 minus 3. Alright, so we're going to color code this like always because I feel like you guys should understand where things come from. Okay? So here's the order. Let me write the order down. 1 is the basic graph. 2 is left, right, shift. 3 is flips. And you have a left, right flip and a up, down flip. Do I want to give you both? Maybe. Okay, we'll see. 4 is a up, down, shift. Alrighty, guys, here we go. Let me start color coding. So the basic graph obviously is an exponential. Okay? So the first graph, 1, I'm going to draw just because I see it's 2 to some unknown stuff, is going to look like this. Too bad they don't have a graph paper thing on OneNote. That would be awesome. Now notice I keep drawing the horizontal asymptote. Now here is the big piece of the puzzle, and everybody needs to pay attention to this. The asymptote is part of the graph. Even though it's a dotted line, it has a position to show that the graph does not cross over a certain boundary. Okay? So if you disregard that, then you've drawn a different graph. That asymptote is so very important. So please make sure you do that. Okay? So now let's figure out where everything is located. Well, guess what? The left-right shift is right here. And this is exactly what you think it is. That +2 like before, that's really going in the opposite direction. So from the basic graph, okay, the basic graph, I did it in red, I should keep it in red. The basic graph, the second graph, number 2, is going to take that basic graph and it's going to shift it to the left 2. So here's what Rush does. He looks at that focal point that we just had, because that's a very important point to keep at, because that's where it starts getting closer to the asymptote before it starts blowing up. That's why it's so important. The asymptote, if you shift an asymptote left and right and it looks horizontal, it's not going anywhere. It's still going to be there. So what does your graph look like? Pretty easy, right? All right, sounds good. That's our left-right shift. Now, do we have any flips? Absolutely, we have a flip. And this is no different than what we talked about before. Where do flips come from? Flips come from these negatives. So this negative right here, for example. That negative is attached to the x, right? So it's flipping in the x direction, which is left and right. So for my third graph, it's flipping left and right. So that means that if we flip a graph left and right, that means if you flip an asymptote, let's talk about the asymptote first. If you flip the asymptote left and right, obviously it's just going to flip over. It's going to appear like it has not even moved. This point that's now at 2, 1 should now appear over there, right? So it should be 2, right? And then check this out. See this little slopage up? That should now be on this side. So it'll be like this, and hit this, and then hug the asymptote. Now, that's a left-right flip. So, yes, we had one of these. Do we have up-down flip? No. But here's the point. If we had one of these, where would it appear on here? Okay? And it would be a negative out here should there be a left-right flip. Okay? Pretty simple. And now, finally, we need to shift down. I will put my last shift in a different color. Gray? Wow, we have gray. How about a different color? I'm running out of colors. Pink. All right. So this is that -3 we were talking about. Okay. So what is the -3 going to do? Obviously, it's going to shift down 3. All right. So here we go. Last move. Let's go back to red. And here's my graph. Boom, boom. Here's 4. Let's take our magenta color where I've lost it and we found it again. All right, so shifted down 3. Now look, if you shift this guy down 3, what is it going to touch? It's going to touch the asymptote, right? The asymptote now officially will move because you're shifting the entire graph down 3, including the asymptote. So the asymptote, which was at y equals 0 still, now we'll make a shift down to y equals -3. And yes, you must have your asymptote labeled. Now, this point that was at 1 will make a shift down 3 as well. Bingo. Now, we need to stick and move. Boom, boom, boom. Pretty easy, isn't it? Okay, so there's still 2 things we need for this, because I'm going to ask you eventually, and that is, how do you find the x and y intercepts? Well, this is no different than what we had before, but we need a little bit of goodness behind it. We need a little bit of juice on how to solve this. So I can't talk about that until we've gotten done with talking about logarithmics. So what I will say is, we will have a recap video at the end of 4.1 and 4.2 that begins like at the beginning of 4.3 that says how to find the x and y intercepts, because we're going to need logarithms. Okay, so here's my point. We will find the x and y intercepts later. Are they necessary? Absolutely. But we just don't have enough muscle yet to do it. Okay, we're just going to shift and move these graphs around to get the general picture. And once we get that, then we can rock and roll. Okay, let's do one more, and I'm going to show you some fanciness I think is fancy, but it's not really all that fancy. Let's say it said graph, okay, f of x equals, yeah, why not? Negative 1/2 x plus 1 plus 4. All right, so this seems really fancy, right? Not really. So here we go. In order to do this one, it's the exact same thing. But you see this? This is a problem. Okay? When you graph these, you want to keep these a whole number, okay, as much as possible, because the 1/2, or better yet, anything less than 1, makes the graph flip around. But why did so? It'll make the graph look like this. Go from this to looking like this. Now the question is why does that happen? Well, this is why. Okay, because this graph right here, it looks like it already has a left-right shift encompassed in it. It does. So what I'm going to tell you to do is do some prep. Okay, I believe in consistency. I'm a firm believer of it. So here we go. 2 to the first power is really 2 to the negative 1. And I'm just going to write the exponent on top of that. Now here we go, back to our laws of exponents. What do we do when we have an exponent to an exponent? Correct, we multiply the two. So this gives me negative x minus 1 plus 4. Now we're ready to graph. Done. This means we're going to have a shift to the right, 1 unit. We're going to have a left-right flip. We're going to have a up-down flip. We're going to have a shift up 4 units. That's simple. That's simple. And all you got to do is run through it. Okay? So this is actually a great stopping point. Use the last example, and I want you to graph this one. We'll talk about it. Talk about later on the beginning of the next video. All right, guys. Like I'd say every time, if you want to go somewhere you've never been and do some things you've never done, you're going to have to really step out of your zone, be uncomfortable, and try to find a way to expand your horizons, okay? You're going to have to do that thing that you've never done before. So this is another Edge. This is Rush Mahaber signing off. I will see you on the next video.